Good morning, everyone. So now we are at session 2 of our day 3 track on microfluidics. Uh, so here
Yeah,
the speaker is Professor Xinghua Ho from
yeah,
National Tsinghua University, Taiwan. He shared with us a talk on machine learning for microfluidics design and automation. Professor Xinghua Ho received the PhD degree in electrical engineering from National Taiwan University, Taipei, Taiwan in 2005. He is a professor with the Department of Computer Science, National Tsinghua University, Hsinchu, Taiwan. From 2007 to 2014, he was with National Cheng Kung University, Tainan, Taiwan, and with National Chiao Tung University, Hsinchu in 2015. His current research interests include design automation and test for microfluidic biochips and nanometer integrated circuits. Dr. Ho was a recipient of the Best Paper Awards at the VLSI Test Symposium in 2013 and the IEEE Transaction on Computer-Aided Design of Integrated Circuits and Systems in 2015. He currently serves as an ACM Distinguished Speaker, a Distinguished Lecturer of the IEEE CAS Society, the Chair of the IEEE Computer Society Taiwan Chapter, the Chair of the ACM SIGDA Taiwan Chapter, and an Associate Editor of the ACM Journal on Emerging Technologies in Computing Systems, ACM Transactions on Design Automation of Electronic Systems, the IEEE Transactions on Computer-Aided Design of Integrated Circuits and Systems, the IEEE Transactions on Very Large-Scale Integration Systems, a guest editor of IEEE Design and Test of Computers. He has presented 10 tutorials and contributed 10 special sessions in ACM IEEE conferences, all in design automation for microfluidic biochips. So now I request sir to share with us the talk on machine learning for microfluidic design and automation.
yeah. Okay, thanks for the introduction. I think I should provide you a shorter bio. Okay,
Yeah.
but I actually, I think you probably need to share the
Sir,
host.
yes, sir. I already stopped sharing my screen actually as a host.
Okay, let me check. But let me check. It seems that I need to release my privilege. 1 minute, please. Okay, let me do it
Yes, sir.
again.
Yes, sir. Now it is visible.
Okay. Let's see if I can use this presenter mode. So now can everyone see my screen, or you see the both two screen or one screen?
One screen, sir.
One screen. Okay. Okay. So let me start. Okay. So I will say good morning, everyone. Yeah, thanks for the invitation to invite me to give a talk. And actually, I worked in this area for many years, and thanks to Professor Krishnendu Chakrabarty, I think he will give a talk in this afternoon in India time. Yeah, he is my strong collaborator, and we work on this design automation for microfluidic for more than 10 years. And recently, we have few research work that apply machine learning technique for design for microfluidic design automation. So, and I also know that I think the Professor Banerjee, and also I'm not sure if Professor Sudhiroy already gave a talk, right? I think he already gave a talk on the sample preparation. So I assume several backgrounds are already provided by them. So I think in my talk, I actually prepare roughly 60 slides. Yeah, 60 slides, and yeah, and I think few slides I will quickly go through, and I will point out some the reference of our paper. So if you want to know more detail, please refer to my paper. Okay. Okay, so before my presentation, as usual, I still need to acknowledge several of my collaborators. So as I mentioned earlier, I have a strong collaborator, is a Professor Krishnendu Chakrabarty from Duke University, and also I think most of you already know him, the Professor Parker Bhattacharya. Yeah, I think he originally in ISI, but now I know he is now in the IIT Kharagpur, and also the Professor Rolf Dressler from University of Bremen, and recently we also work on the open source digital microfluidic with Professors Changjin Kim, the CJ Kim in UCLA, and through the introduction, I think the host already mentioned that we have a best paper award that collaborate with the people in Stanford University. Yeah, and the professor there is Stephen Craig, and also Professor Paul Pop. Yeah, he from Technical University of Denmark. If you are interested in the control logic and also high-level synthesis for microfluidic, you can read his paper. And one of my another strong collaborator is Professor Wolf Schlichman from Technical University of Munich. Yeah, we for flow-based microfluidic, we actually developed a tool set called the Columba. Yeah, it published in ICK and DEC in the recent years. So if you are interested, you can also refer to this paper. And there's another microfluidic chip made by paper. So most of the microfluidic chip, the substrate are PCB glass.
Sir.
Yep.
Sir, I think your screen actually only showing us the first slide of just in normal mode, not in presentation mode.
Oh, really?
Yes, sir.
Oh, strange.
Yes, now it is moving, but not in presentation mode. It is showing in normal mode.
So it's not full screen.
Yes, sir.
Oh, strange. So now can you see my slide?
Yes, sir, I can see the slides, but the slide is in normal mode. That means that the way we prepare the slides in that mode, not in the presentation mode. Actually, now it is.
Ah, okay. Strange. Oh, really. How about this?
Now it is fine, sir. Yes, sir.
Oh, okay. Okay, so I'll go ahead. So
yes, sir.
Oh, thanks for the reminder. Yeah. So if you are interested in the paper-based microfluidic, you can talk to the Professor Kwang Woo Sin. Yeah, he can print the substrate by the printer and using any kinds of papers. So that's a very new technology, and we also have several collaborators from Austria, Professor Robert Wieder, and also the Professor Shigeru Yamashita from Japan. He also, yeah, I know the theme of our workshop is also include the quantum computation. So Robert and the Shigeru Yamashita, they also work on the quantum stuff. And also the Professor Hailong Yao, I think in today's talk, I will mention one collaboration work that we published at DEC last year. Yeah, and also there's some support from the Duke, Stanford, and also the company Advanced Liquid Logic, and now the company of Illumina. Okay, So now I will quickly go through the background for the microfluidic. I think the reason why we are using the microfluidic, I think already few speaker already mentioned about this. Yeah. So first is of course the bioassay operation are now very complex, right? So people probably heard about the Moore's law. That means the transistor size will double every 18 months. But for microfluidic, they also have a Moore's law for this. Actually, they are defined by a company called the Fluidigm. Yeah, but here I show the slide is called the Moore's law for experimental biology. That means the number of biochemical operation will increase significantly. And if you want to perform these biochemistry experiments, you also need skilled technicians. You know, they are very expensive. They are well trained, but they are expensive. And you need to know that most of the experiments are actually very tedious. You need to spend a lot of time to do the hand working experiment. It wastes a lot of time, I would say. And also you need to purchase the bulky equipment, right? So with this, that's the kind of the roadblock that people did not use did not have the chance to implement a very complex biochemical experiments. So if we can have something that string everything together, we call it a lab on chip. That means that we can integrate a technician. It's like a I don't know if you see the animation in Japan called it Doraemon. You know, you can have a flashlight that flash these equipments, and also the technician that string to the tiny scale and into a small biochip. Then with this small biochip called the lab on chip, and now we are talking about microfluidic technology. Then you can achieve several objectives like high throughput, minimal human intervention. Yeah, and because everything are automatic, and because it's very small, so the sample reagent consumption is very small, and everything are automatic, so it's highly sensitive, and the productivity is, of course, it will increase. So the reason why the microfluidic chip is very small, the one of the most important objectives is called the high throughput. Yeah, so in this example, I want to show that if you want to perform 1 million bioassays, and each bioassay is just consists of a 10 microliter format. It's very small, but if you consider the 1 million times, then you will totally need 10 liters of reagent. You know, it's like several bottles of water, something like that. Yeah. So, and if you need a 10 liter reagent, that actually is very expensive. Even big pharma cannot afford this. So yeah, because and also if you need if you cannot achieve this high throughput objective, then you probably need several staff, as I mentioned, very expensive technicians and also equipment to do these experiments. Actually costs a lot of money. So in this slide, I show you in the bottom side. This figure actually shown provided by the people in the EPFL, and it shows that several variable materials, and of course the diamond per grain is the most expensive. But if you look at the upper side of this figure, you will see several biochemical samples are actually very expensive. For some antibodies, sorry, I'm not sure why this slide has the top upper part has been cut. So this part actually shows antibodies. So some antibodies per gram actually is more expensive than diamond. So you think about that, if you would perform a lot of biochemical experiments, you need several samples, and this sample actually very expensive. And also it's not right. I think most of the audience are with the computer science background soon. So you're writing several codes. You do programming and writing codes. And in computer science area, most of things are Boolean. right? It's either 0 or 1, yes or no. But in biochemical area, there are several gray area. It's not just 0 and 1. It's several experiments you need to perform multiple times until it collects sufficient information. Then you can do the statistics to make sure that the experiment is correct. Okay, so before that, you probably need several samples. Actually, very expensive. And yeah, there are several kinds of biochip. So I think you probably heard about the in the past, people are talking about a microarray, DNA array, protein array. They can do this DNA or protein computation. But this microarray, they are passive array like. It's like a two-dimensional array, and you can put the sample A in one of the wheel. I mean, if you look at the array, it's like in the element. Okay, you put sample A there, then you can put sample B together. Then after a while, you will see A and B they mix together, and you will see the result is good or not. But it's very passive. You just put it in, blend in, and wait the result. But for microfluidic biochip, here I show here is called the active biochip. Yeah, it's more like a you are not just put two sample together. Actually, the sample can flow inside the chip, and also you can make it programmable. You can make, okay, this time I want to do the experiment A, this time I want to do the experiment B, and you can do you can use some programming technique to control the behavior of the biochip. So microfluidic biochip actually can do several experiments at one time, and also they can have a decision control. They can have even in the future. I think in today's talk, I will not talk about this. It's called the cyber physical integration. You can integrate several sensors and control logic and everything into one biochip. So so today I will talk about this microfluidic biochip, and there are two major kinds of microfluidic biochip. So today I will talk about we'll try to apply machine learning for digital microfluidic biochip, especially for the routing task, and for the continuous microfluidic biochip that here I showed. The continuous here means that the samples are flow continuously. Yeah, and you need several channels, flow channel to carry this sample to flow. And for digital microfluidic, the sample are carried by a small payload called the droplet, the very small, tiny drop, and this tiny drop can move to any place by your programming control logic. Okay, so yeah, so this microfluidic biochip also can do a lot of applications. I think the previous speaker, I think, already mentioned this. They can do clinical diagnostic, is environmental monitoring, and also do the drug discovery. So I think also right now, I hope everything, every audience here and your family are well because of this COVID pandemic. Yeah, so because of this outbreak of COVID, so several people now try to discover the potential of microfluidic to do the COVID test. So in the past, people are doing the serology test. Actually, the result is not very good and also take a lot of time. And if you want to do the high throughput, yeah. So for example, right now, I cannot share my camera because I'm currently in Hong Kong. I actually in Hong Kong, and I'm in the quarantine hotel. The Wi-Fi quality here is not very good. So when I landed in Hong Kong, and I need to do the screen test, right? I need to do a PCR. So I actually arrived last Sunday at roughly 11 p.m. And then I because I know I need to do the PCR test, so I run very fast. Yeah, when I get off the plane, I just walk very, very fast because I saw I can do the test as soon as possible. Then I can get out of the airport very soon. But when I landed in 11 p.m., I actually wait till wait roughly 3 hours. I actually get out of the airport at 2 p.m. 2 a.m. Yeah, because I do the PCR test, and then most of the passengers are waiting for the result. Yeah, so that takes a lot of time, and if you cannot do the high throughput or even do manipulate a very tiny sample, yeah, that actually, yeah, it's actually very it's not very convenient. Yeah, and also, and recently there's a company called Microfluidics. Yeah, they try to they mentioned that they try to double their manufacturing capacity to meet the demand of microfluidic. So how to do that? Yeah, again, you need to do the first. You can do the larger scale microfluidic. Another one is that you can use some software tool and packages help them to design the microfluidic. Yeah, so that's why so in the past people are talking about the microfluidic very large scale integration because applications are getting more complicated. Yeah, because we need a large scale bioassay and several assays need to operate at the same simultaneously on a biochip. And the design complexity increase, so you probably will face several electrodes. So in this example, I think this video has actually come from the babies. Okay, actually babies is originally the advanced liquid logic. They are located in the North Carolina. So as you can see in this video, the droplet can dispense from the dispensing port, and the droplet can move, and they can merge, and they can do incubation, everything on one chip. Okay, and now you see several small rectangle, and last is the electrode. Okay, this is the arrow view for the digital microfluidic. So here, think about it. If we have 600,000 electrodes on a biochip, that will actually very complex. And in the left video, you just see one droplet move. But if in the right side, you can see many droplets are moved at the same time, right? And so the problem is, how do you control this droplet move from their source to their destination without any collision? Yeah, so because as you can see here, each droplet have there is some space between any two droplets, right? So because if two droplets, because they are liquid, if they are too close, they are because of this surface tension, several physics phenomena, the two liquid will actually merge into one, right? So when you manipulate the droplet to move, you need to make sure that they maintain some distance but among all the droplets. Okay, so the droplet routing problem actually is not easy. Okay, so to design this large scale microfluidic, so in the past, we already have many researchers working on this synthesis flow. So the problem is that if we want to conduct a bio experiments, that in this example we have in the upper left figure here, it shows a sequencing graph. We have 6 operations here. So operation 3, operation 6, they will dispense from the dispensing port, and then will come to operation 5 to mix. And operation 5 and operation 1 will come to operation 2 to do a second mix. Okay, the second mixture, and after that they will move to the operation 4 for detection. Okay, so that's the procedure. This is called the sequencing graph. So that illustrate the bio experiment. Okay, so in the past we just say, oh, we need to do something writing in the lab book, and now we can use the graph model it. I think if you are a computer scientist, you know this graph representation, right? And because in this example, we probably have several mixer. Okay, so operation 3 and operation 3 and operation 6, they will mix together, and you can choose a larger mixer. Right? I will provide more area for them to mix, or we can provide a tiny area for their mix, but different size of area, they will consume different time. So we will provide the library for them, and then then when you design the microfluidic chip, of course you need to provide a design specification. That means that all the experiments in this example, we need to make sure all the experiments are conduct within the 5x5 array, and all the experiments need to finish within the 50 seconds. So you can think about that. If we can have a very big biochip, then we probably can finish all the experiment at the same time, because we can do experiment at the left hand side, experiment B in the middle, and experiment C in the right side, right? You can fully utilize the area, but now the area is limited, and the area is limited, and then we have a different size of the mixer. So you need to do some optimization. Which one is better, and which one need to do first? Okay. So based on this information, then you can do the architectural level synthesis or coded high level synthesis. Then each operation need to find to bind the actual resources from the module library. So this is called resource binding, and then they will determine the schedule. And in the first time step, operation 1, 6, and 3 will conduct first. Then after that, in second time step, you will conduct the operation 5, something like that. So based on that, you will have a very high level estimation on the if this is doable, and also roughly the time. I mean the execution time for the chip. Then after that, then you can perform the physical level synthesis. Like that means that we have 6 operations. You need to determine where are they located, where are they placed. Operation 1 here, operation 2 here, and so on. Then after that, then you determine the routing. That means the operation need to they are droplet in the operation 1, they to move to the operation 2, something like that. Okay, so this is called the physical level synthesis. Okay, so now I think for today's talk, I mainly talk about one problem according to droplet routing. So droplet routing, if we take a close look at this droplet routing problem, the input are a list or droplets, a net list or n droplets. That means we have n droplets, D1, D2, and 2 till Dn, and the location of several blockage, the big B here, and also the B1, B2, we have M blockage, and also the timing constraint Tmax. That means all the droplets should route from their source to their targets within the timing constraint Tmax. So in this toy example, you see the left hand side, you can see we have 6 source. Source 1, source 4, source 3, source 2, source 6, source 5 here in the yellow rectangle, and also we have 6 targets, and they are marked in green rectangle. So the objective is to route all the droplets from their source to their target while meet the constraint called the fluidic constraint and the timing constraint. So fluidic constraint, that means I already mentioned that 2 droplets cannot press too close. They need to keep a minimal distance between 2. Okay, if they are too close, they become the bigger one. So if these 2 droplets are placed here statically, now that means that it's called the static fluidic constraint. If these 2 droplets in the right side either these two droplets are moved simultaneously to the left-hand side. So in the in between the movement, the droplet could probably mix together, have some unavoidable mixing. So this is according to dynamic fluid constraint and timing constraint. I already mentioned that all the experience need to finish, all the routing need to finish within the Tmax. So the problem is like this animation. I will show you an animation like this. We have 6 droplets from their source to route to their target, but you need to make sure the droplet will move to their target successfully. In during the movement, they will not cause any unexpected mixing. And of course, the objective is we will try to minimize the total routing time. Okay, so in this problem, I think in this problem formulation, already several researchers are working on this, and I also know several famous researchers in India also working on this problem. But for this routing problem, now I was going to talk about why we will consider to use the machine learning to solve this problem. Okay, yeah, because these digital microfluidic biochips have very severe reliability concerns. Yeah, so as I mentioned, there's a big giant company called Illumina, and which is a leading company on the DNA sequencing, and they actually hold a sale of NeoPrep. NeoPrep is actually a sample preparation tool made by digital microfluidic. Okay, but they stopped because the reason for the stop is because of the reliability concern, and also the electrode. If we actually several times, because this digital microfluidic, on top of this electrode, you actually need to do the coating, and the coating, the thickness of the coating actually play a very important role. Okay, and if it's too thin, because the droplet movement, if you want to do the droplet split, you need to trigger very high voltage, and this high voltage will make the very thin coating to break. Okay, yeah, and if it's break, actually it's a mechanical break, then you know you are not structurally the chip that has a problem. It will not function. And yeah, so actually the thickness of the coating, for example, Teflon coating, and also the high voltage will cause the electrode degradation. Okay, so if that problem is not as severe, the droplet will stuck on the degrade electrodes. So in this figure, you can see in the left figures. So the original, I'm not sure everyone can see my my cursor. Okay, so originally the droplet is located in the left hand side. It shows the degrade electrode here. Yeah, we want to move to the right side, but because it's a degrade, when you apply the higher voltage in the right side, supposedly the droplet will move to the right side, right? But because this the left side the electrode is degraded, so the droplet actually cannot successfully move to the right side, and they still leave some residual in the left side, left electrode. Okay, so that's the problem. So how do you solve this problem? And but the problem, the most difficult thing is that you cannot predict which electrode are degraded. You know, it's not like you cannot just simply do a camera to look at, oh, the droplet already moved to here, the droplet become bigger, droplet become smaller. If you use the camera to take the several shot on the electrode, you cannot tell, okay, this electrode is degraded or not. You know, it cannot tell from their appearance. So how do we do that? Yeah, so we want to, because the electrode have some degradation effect, so we want a smart droplet routing algorithm that such droplet routing algorithm can perform the online decision making. So when they move, so in this example, you go to the left, go down and go to the right side. Yeah. So here you show in the middle figure, you can see many this orange, light orange electrodes. They are either moderately degraded electrode or the very severe degraded electrode. So if this droplet go to the downside, most likely droplet will stuck somewhere, or they probably will move very slow to the destination. So in this case, I hope droplet can do the smart routing, go to the upper left, go to the right side, and go down to the destination. Okay, so we need to do the online decision making. We need to learn from the past experience. Okay, so how do we do that? So we are thinking about to use a famous technique in the machine learning area, like called the reinforcement learning. So I will not go through too many detail here, yeah, about AI or reinforcement learning, because I think there will be the big. Honestly, I'm not a people working on the machine learning area. So typically for us and for me and my students, we actually leverage the several technique from the machine learning, especially IO, reinforcement learning area, and to apply to the microfluidic area. Okay. So the problem is like that. If you are the machine itself, for example, like our router, yeah, it's like an actor. Okay. And we also have the environment, we call it the state. We have several state. Okay. So the reinforcement learning is that you can receive you can actually observe and receive some information from the environment, then you will react and to generate an action to see what's going on, right? So you do something, then you will see then when you understand the environment will change a little bit. Then based on that, it's like a cycle. Then the new environment will provide the input, the observation to the actor, and then you need another action. So it's like that you provide as a loop. You receive several information from the environment. You based on the environment, then you decide what to do. Okay. So the action is more like the functional output, and the actor will provide a lot of action. The action is actually like a function that based on the input is based on the observation, as I mentioned earlier. But the most important thing is that we want to know the action is good or not. So it's like you learn the bicycle, to ride a bicycle, right? You turn yourself to the left side a little bit or right side a little bit, and this time if you did not fall down, that's a good action, something like that. You can try to do that, and the fall down itself probably is based on the reward. So if you can ride your bicycle from here to the front side, maybe 5 meters or something, then that means that you gain a very good reward. That's the objective. The reward can be like, okay, if you did not fall down, or you can move forward, something like that. You can define several kinds of reward. So the definition of reward is very important for reinforcement learning. So based on the reward, then you can decide the new action. Then feedback to the environment, then you can do the loop several times. So the reinforcement learning, the most important thing is that we need to try to find the polish and to maximize the total reward, because it's not just a one time, right? Our target is to ride the bicycle to the 5 meter away, right? 5 meter away. So that does not mean, oh, okay, right now you can move in. That means it's already good. And also the reinforcement, the biggest difference between the reinforcement learning and the pure, people probably know the pure deep learning, like the convolutional neural network, is that you probably think, okay, this is something that convolutional neural network. For example, if we are doing a routing, we are given current state. Now droplet is located in the source. It locate a source point, and then you can put it as an image, right? And then you will predict the result to the move to the right, to the left. Then you can decide you will go up, down, or left or right. I think it's simple, right? It's like a classification problem, like convolutional neural network. But reinforcement learning, the biggest advantage of reinforcement learning is that they can do better prediction. So convolutional neural network is like you in a certain step you will know, okay, go to the left side is the best because your target probably in the left side. So in the current step you move to the left side, to the left electrode is good one. But actually in the real but because we are considering the electrode degradation, so now if you move to the left side, indeed the target is in the left side. But if you go to the left side for the first step, doesn't mean it's the best one. You know, yeah, because you need to consider the environment will change, because multiple droplets will come in and you will not know what will happen in between. And in this case, the environment will keep changing. So at that time, you will consider to use the reinforcement learning. All the problem will simply just use the convolutional neural network to solve it. Okay. So this is I think I'll skip very fast. So this is another slide talking about reinforcement learning. It's like they play the game. I think there's a very old game called the Space Invader. And I just want to let you know that the actor actually is more like the policy network. It's the deep neural network. The actor actually is like a deep neural network. Okay, so if in this example, if you want to hit the aliens on top, then you can do the left side or right side, or even do the fire, right? And the different behavior, we have a different score. They call it a reward, right? Then you feedback, then go to the left side, then you will see, oh, the result is good or not. Then you will do another run. So you do several runs. So that's the reinforcement learning. Okay. So that's the basic introduction on the reinforcement learning, and now we will try to use the reinforcement learning that I will call IRO in short, to use the IRO to do the droplet routing. So the experimental setup is like this. So we have a digital microfluidic biochip. So we have a camera on top, and then we take the video, not the video, sorry, the image, okay, back to the controller. So we use the Raspberry Pi to collect the image. Then the image will transform to the RGB file as the matrix input for this IRO agent. Okay, the IRO agent will update their weight, then take action. Okay, they tell you that okay, the droplet needs to go to the left or right or up and down or something, or still at the original place. Yeah, they'll decide the different action back to the controller. Then back to the controller, then controller tell you, okay, the electrode need to do actuation to move the droplet. Then droplet move, then you have a new state, and you have a new observation. Then you do again. Go to the collect the image, go to the network, update again, and so on. So when you take the action, move the droplet, then you will receive a reward. Then you will decide, okay, the action you did earlier is good or not. Okay, so the problem is actually very simple. Like we move the action is try to move any adjacent electrode. Then the state is the location of the droplet occupied electrodes destination, and the reward is that if the action will lead to the closer to destination state. Okay, or you will push the agent. Okay, so but the problem is like that Yeah, so I think we actually do two things. We actually try to use the IO to decide to develop the droplet routing algorithm. Okay, and we will do this first, and then the droplet routing algorithm will become like a model, a neural network model. Then we will try this routing algorithm on the degraded digital microfluidic biochip. But the most of the we cannot, because you probably know that if you are performing something called a machine learning algorithm, we probably need a lot of sample to do this. But it's not possible. It's not always possible to do this because we need to use several real chip to do the test. We try many times, and oh, this is good, this is not good. Yeah, but when you're doing the training, you are actually wasting the money at the time. Okay, so what do we do? So we actually use an API from OpenAI. We construct something called the OpenAI Gym. Actually, it's a virtual environment, and we put some manufacturing parameters to formulate the real degrade situation for I mean the degrade information from the real chip, and we input this information to a simulator. Then on the simulator we can do we can simulate the droplet routing, like considering electrode degradation for many times. Okay, so that's how we are doing. So again, the transition model is like we can go to the north, south, east, and west, and the reward function is that if they are moved closely, then we will get a reward, like we get some bonus. If they are to the far to the opposite direction, you will get some punishment, and if you did not move, you will also have some punishment. Yeah, so that's how we define the reward function. I think this is very tedious, I would say. Yeah, if we did not define the reward function very correctly in the past, my student told me the droplet just make a route in a circle. They will never move to the destination, and also the droplet probably will just move to the boundary of the chip. Yeah, then you stuck there, something like that. Yeah, so we need to do several types of training, and so for our training, we actually use we only do a very tiny, very small convolutional network, 3 convolutional layer and 2 fully connected layer. Okay, at the end, yeah, and to do this actor, the neural network, then to how do we consider the gradient approximation? We actually using the proximal policy optimization, PPO. I think it's very commonly used in DeepMind and also OpenAI. Yeah, so we based on this method to develop our routing algorithm. So we also try several benchmark, several situations based on the 10 by 10 to the 65 by 65, no, so not 35 by 35 electrode arrays. And the baseline is based on the heuristic droplet router. The agent is the router that defined by our algorithm. So after several training epoch, then you will find out the droplet routing algorithm is very close to the baseline algorithm. That means that we can really automatically to route from their source to their destination. So here I show a video. Yeah, very quickly. I think this work actually is done with Professor Krishnendu Chakrabarty. We collaborate on this topic. Yeah, and the paper actually published in the ICML last year. Yeah, so that is very simple. We just consider one droplet. from their source to destination. So droplet will suddenly disappear. It go like this back and forth, and did not know what they are doing. Okay, but after a while, after a few epoch training, the droplet can know where to do. Okay. So in our algorithm, we are not just consider simple source and to target. We also consider potentially the concurrent module. That means the blockage in between the source and target. Yeah, the lower one is the blockage. But as you can see here, they are still not very good. They are still not find the shortest path to their destination. Yeah, I think I will speed up. So after several 300K several times, so I say this is not possible to do it on the real chip. So we need to make a very sim to real simulated environment. Okay, so at that time the droplet can move to the destination, use almost the shortest path. Okay. Okay, I'll skip this. Yeah, and if we consider the degradation, the traditional, the baseline algorithm, they are just simply do the shortest path droplet routing algorithm from their source to their destination. But if they face the degrade electron, the droplet will try to move to the degrade electron. They will try many times, and but if it's not work, then you maybe just stop. Okay, and so or you will find you will make a detour to find the degrade electron to the destination. So based on our algorithm, our IO algorithm that considering the degradation, they kind of they predict which electron will be degraded. So the droplet when they move, they will automatically bypass or find a detour, automatic detour to the destination. They bypass this degraded electron. So here, as you can see, we only use if 10% of electron degrade, 50% or 90%, even 90% of electron degrade over time. In this very tiny 10 by 10 digital microfluidic, and you can see that our agent can actually route less wavelengths than the I mean less of number of cycles. I mean less of the actuation cycles from their source to destination. Okay. So here I also show you another the video. Maybe I make it quick. Yeah. So originally as I mentioned, we already have a droplet routing from source to destination. Did not consider the degrade. Then we use this model that consider the degrade electron. So in this simulated environment, they will know if we are facing the degraded electron, what will they do? They learn from this observation from the environment. Yeah, so after several 500K, so they will learn because the electron actually is not degrade immediately. That means that if you are some electron, if they are triggered by other droplet, right? They will after several times the electron actually will degrade. Okay. So because when you are doing this droplet routing, you will not know that they will degrade so fast or so long. It's not just a static. It's not like an equation that you know. Okay, 5 times. If they are actually 5 times, then you will know that you already degrade. It's not something like that. Yeah. Yeah, so I think I will skip this. So after that, so after several IO training, the droplet routing they will avoid to use this degrade electrode. Okay, yeah. So that's what we are doing. Yeah. So this is this slide shows the experimental setup. I will not go through the details. So we typically have yeah, as I mentioned, we do this is the small one of 6x6. Then but the largest one is a 65x65, and also the voltage amplifier. Yeah, I think, but we still use the 200 volt, and we connect to the microcomputer, the Raspberry Pi to control the digital microfluidic biochip. Yeah, so this is a real case on this. So in the left side, the agent actually experienced that if we know this electrode, marked in red is already degrade, then the droplet when they are doing a move, in the later routing test, when we know that this has been used and also already degrade, they will automatically find a new way, new pathway, new routing way to route to their destination. So we actually try it on some real cases from the nuclear some immunoprecipitation assay. Okay. Yeah. So that's good. We actually use the reinforcement learning for this droplet routing. Okay. And then now we are considering to use the different microfluidic biochip. Maybe some of you already heard this from the previous speakers. Called the microelectrode dark array, the MEDA biochip. Okay, so the difference between these two biochip is that the electrode actually is more fine grain. So in traditional digital microfluidic biochip is more like a typically array style, and the droplet can move to the left. Each droplet is triggered by one electron. But now here, the electrode is very small, called the microelectrode. So a droplet can be triggered by multiple electrode at multiple microelectrode at the same time. Okay, so with this fine grain control, the droplet can move in any direction. In theory, they can move to any direction. And when you are doing the splitting, you can have a different size of the splitting, and yeah, you can perform multiple experiments on such a different way, different experiments on such a MEDA biochip. And the MEDA biochip is different from the traditional digital microfluidic biochip that purely use the PCB glass as a substrate. Because MEDA, they actually on top of I would say below the electrode, there's a shading layer. The shading under the shading layer, you can have several CMOS circuitries to control each electrode. So in currently our collaborator, the Professor CYD from National Jiao Tong University, they actually use the 0.35 microliter. No, let me think. Yeah, 0.35 micrometer process, CMOS process to do this to do this fabrication. So because each electrode underneath each electrode, you will have a control and detecting circuits. You can detect the capacitance of each electrode. Then you will know the droplet is on above the electrode or not. So in the past, if we want to know the droplet, if the droplet is successfully moved from their source to destination, we need to use the camera to know, okay, where are the droplet. But now with this I would say sensing circuits, then you can know, you can detect the location of each electron or each droplet, yeah, at any time. Okay. So here also show the video that you can see So this is a one droplet move, and the multiple droplet they can do the mixing, right? And yeah, it's a you can the droplet can do several kinds of the formation, so that's good. That's a meta. They have several advantage, but okay, but if you look at the bottom side, again, they will also face the degradation issue, and also I have to say that the degradation issues in meta actually is more severe than the traditional digital microfluidic. Yeah, so if there are some microelectrode there, now we have many microelectrodes, but if one microelectrode is fail, degrade, then you're missing your movement, everything will be wrong. Okay. So if we look at the previous work that I published in ICML last year, yeah, there are some limitation. That means in the last work we assume only one droplet move. Okay, and also even we consider the blockage. I mean the concurrent assay. This unconcurrent assay actually need to be stationary. That means that they are still in somewhere. But in reality, the droplet will move. Multiple droplet will move. They'll always move. So the previous assumption actually is quite simple. Yeah, kind of a little bit conservative. And also the previous digital microfluidic need a CCD camera to locate the location of each droplet. So, but with meta, we can, as I mentioned, we have a sensing circuit, so we can sense the result at any time. So to consider this parallel droplet control, so we consider to propose to leverage the power of the multi-agent reinforcement learning. So the different from the one, I think you can see it looks like a simple extension, but actually there are lots of tedious parameter tuning and the cost function combination for this multiple agent reinforcement learning. So again, we have many actors. Okay, we will observe from the environment, and also we will receive a lot of reward, and then they will produce the action then to the environment. Okay, then originally we try to use there are three commonly used reinforcement learning algorithms. I will not go through the detail here. So typically the DQN, PPO, and ACE are the actor critic. Actually the off parachute. That means that they are trained in different model. So we use the ASER, PPO, and DQN to conduct this problem. Okay, and because we have multiple agents. So how do we do? So we actually tried three different framework. One is the centralized network. That means if we have, for example, if we have 5 droplets, and then we have 5 actors, so we can these 5 actors will use the unified neural network. Is centralized, but as you can imagine, it's very big. So computation they actually is very slow. Okay. So another one is the concurrent. That is very simple. That we have each agent they maintain their own neural network, their actor. Then based on the result, and then they'll collect together and then perform the action and for the environment. And also we can also try to use another non-intuitive way to try to use the parameter sharing. That means we also maintain one neural network, but it's not like the centralized one. The centralized one is to concatenate everything together, but the parameter sharing is use only one small neural network. So it's like if we have 3 droplets, then one droplet have maintain one neural network, then the second droplet will use the same neural network like the first droplet. They are all use the same neural network, but they are trying to share the parameter. They just update the parameter and to save some space. and try to see if they can perform a good result. Okay, so the procedure is pretty much like the previous one. So in our ICML paper last year is only perform the droplet movement to the 4 directions, and actually also have a steel. Okay, actually it's 5, and now we consider the 8 directions also including steel. Okay, and the input is again also from the sensing result, but it's not from the sensing result is not from the camera. Okay, and then we'll do the multiple agent to see how it reward, how it action, and how it feedback. Okay, so here I will not go through the detail because actually, you know, we published this paper in the ICML. Both papers are published there last year and this year. So this paper actually, the machine learning conference have some a little bit different from the one in the EDA conference. They actually need to provide a lot of separation studies and a lot of experiments. So here I don't think the experiment is that interesting. So I will not talk about go through the detail of all the experiments. So if you are interested, we can discuss or you can refer to our paper. So we actually use another API called the Petting Zoo from the University of Maryland. Yeah, again we generate a virtual environment and try to test our droplet router. Okay, and the actor is different. We have a 6 convolutional network and one fully connected link there, and we try to implement different IO algorithms on different training scheme. Yeah, so among all the experiments, we realized that the DQN result actually is not very good, but PPO and ASA can in some cases they can converge like the baseline, I mean the heuristic algorithm, and but in different framework, the different scheme, the centralized concurrent and parameter sharing during our experiment, the concurrence work best. Okay, so finally we adopt the result using the concurrent neural network. So again, I will show you a video. Yeah, you have better understanding of what we are doing. Yeah, so we should do a lot of tests again. Just like we need to train the router, multiple droplet router. Actually, there are already many papers are working on this. In the past, there are several heuristic algorithms on this, but this time we use the IO to do this. And here also this slide also shows some parameter setting, like how long the electrode will degrade it, and the percentage, the probability to do degraded, and also the with a binary random variable to show that the density of the on the meta array. Okay, so if we consider the result here, the PPO and also ASA, they work. I think they work. They compared to baseline, they work better. Yeah, because they have better score for this. Okay, so I think here I will show you I'll show you some BioSA execution on the fabric and meta chip. I think it's a more complete one. I can give you a better understanding how we are doing. Actually, we need to set up everything. Meta chip, actually, the student even fly to Taiwan. He is a student from Duke. He fly to Taiwan to conduct all the experiments. Yeah. Yeah, the single agent is the previous work in ICML last year. So here I show this the title of these two papers. If you are interested, oh, what's going on? Okay. Yeah. So you are interested in these two work, please refer to these two papers. Okay. Yeah, but here I can give you some extension that probably you can consider. So in our paper, we still consider the unit size. Yeah, MEDA actually can perform multiple size of droplet. Okay, and it can route to any directions. But here we only consider 8 directions, and the size of the droplet actually are the same. Okay, so if the droplet size are different, the network will be totally different. Okay, so we did not consider this. I'll let everyone know that, and that would be the that would be an extension that you can working on, because you know, that will fully utilize the advantage of MEDA. Okay, I can. Yeah, so I think I will skip the you can move multiple droplet from the associated target, and yeah, so you can do a mix everything. So yeah, so I will skip the video here. Okay. Yeah, so now I finished the talk or the digital microfluidic. Now I'll quickly go through. I think we only have 90 minutes, right? So I probably have 10 minutes or something. Okay, so so another talk is about flow-based microfluidics. So here again, I will not go through many details, but I just want to tell you that what we are doing for this research. So digital microfluidics, as you just know, that is made by the two-dimensional electrode array. The samples are carried by the small droplet. But here, for flow-based microfluidic, you actually have several flow channel, like this video shows. They are doing perform the rotary mixer. So you have several channels. The samples are flow like this, and you have a simple flow to the flow channel. Okay, then you can control the valve. So in the rest of my presentation, we did not consider the valve-based continuous flow microfluidic. We just consider the traditional PDMS-based flow-based microfluidic. I think my collaborator, the Professor Parker Bhattacharya, he also did a lot of work on this flow-based microfluidic, and they also use some technique to accelerate the simulation speed. Yeah, but both of us, we did not consider the valve. So this is the open area. So we haven't considered to design to take the valve into the consideration. Okay, so yeah, I think I will go through. I will mention this later. So flow-based microfluidic, again, when we decided, we actually need to design multiple times. Okay, so when you identify the application for microfluidic, flow-based microfluidic, then you need to use AutoCAD to draw the design. Usually use the AutoCAD. Then you fabricate. If the result is not good, you redesign. You do multiple times. To my understanding, they need to do more than 20 times or something to until the chip is good. But you know, you need to design many times. Even you need to fabricate. Even you need to do the simulation. Yeah, I think that's take a lot of time, very tedious. So in the past, there are some researchers that are thinking about probably we can use a library to generate library for all of them. So actually, right now there are still research group in Boston University and also MIT. They are working on the, I forgot the name of the, called the Metafluidic. I remember Metafluidic. They actually have the website, and another called it the 3D Microfluidics, 3D Micro F. Yeah, it's in Boston University. The Meta Microfluidic is in MIT. They try to make a website that they collect a lot of already designed microfluidic chip there, and also several components, for example, like the splitter, mixer, and so on. Okay, then if you want to design a bigger flow-based microfluidic battery, you can utilize their library. Yeah, because they are already test, and also they also stimulate. So then for such a library, you can predict how they work. Okay, so that sounds a good idea if we have a library for all possible chip design. But the problem is that you need to do the stimulation for many times. Even general library is very tedious, very troublesome. If we look at a very simple chip, this chip are doing the concentration generation. I think the speaker I think the previous speaker probably mentioned similar things. Okay, so this is two input. Okay, we have one input is 100% of the sample. Another is 0%. I mean the buffer or water. Okay, then we have two output, and here we have a four turn point, and we have four possible channels in between. Okay, so in this case, in this small case, we probably have we will have 16 combinations, right, like this. Okay, so even this very small 2x2 grid, yeah, you already have 16 combinations. Okay, so if the channel is fixed like this, then you can predict the output here it will be 100% and 0%. But if we remove this channel 2, okay, it moved like this, then the left hand side, this number 2, the left hand side will be the 74%. The concentration will 70%. The right side will be 6%. So based on the different combination of the channel, they will have a different result. Okay, so it turns out this 2x2 grid will support 7 different output concentration, because some of them they are broken, they are disconnected, they will not produce any result. And even if they are produce a result, some are actually very common. But I have to say that this is only 2x2. Okay, so if we are think about more complex one, in this case A by A, then you need to consider lots of several enumeration. There you need to consider several possible different chips to do to build out the library. It's almost impossible. Okay, so not to mention that you need to do the simulation. So actually this work actually I also collaborate with this professor, Professor Junchao Wang, and so he published this paper in Lab on Chip Journal in 2016. So they try to randomly generate more than 10,051 3 random chip, and it takes 3 weeks, okay, to simulate, okay, and to simulate all the possibility, and in each possibility you need to use the console. Actually, the console is the fluid dynamic flow simulation tool. They actually consume a lot of time. Yeah, so it takes a lot of time. How do we do? So the procedure is like that. Like I mentioned, this is another slide. They they use they design use the MATLAB, use the console to the simulation, build out the database, and the database is more than 10,000 simulated design. The whole procedure needed 3 weeks. Then you can use the MySQL data to create a database and return the result, and based on your result to do the design. Okay, that's very fast. So the paper is published, as I mentioned, in Lab on Chip 2016. So in DEC 3 years ago, we published a paper using the artificial neural network. Okay, but the problem, in this paper we actually have 2 contributions. One is that we use the artificial neural network to do this. Okay, and the second thing is that it's different from the previous work. That in previous work they consider 2 input, 3 output, very simple architecture, and A by A. Okay, internal structure is A by A, and 2 input, 3 output, 2 inlet, 3 outlet. Okay, and for the previous work and even this work, the flow rate, the flow rate from the input, they are all the same. But and the outlet length are all the same. And so 3 years ago, we consider if we can adjust the outlet in different lengths, then we probably can generate a different concentration. Okay, so that's a new. So we consider the different lengths of the outlet and try to do more concentrations. So in this case, in the past, we need more than 10,000 chip. So in 3 years, okay, I would say in DEC 2018. So we actually just need to train 272 and artificial neural network, because by this extension or this outlet, we can cover several kinds of situations. So it turns out we only need 272 artificial neural and actually a simple deep neural network, okay, to do this, okay, and get to the better result. So originally the random design, the Day-3 chip, they cannot cover all the concentration requirement, and even for this DEC 2018 paper, and each artificial network need to train, but we only, although we can reduce the size to the 272 artificial neural ANN, but each ANN need to train 200,000 samples. I mean the different sizes or the outlet. Okay, so the total training time, actually, when you build out the database, you still need several days, 188 days to do the training. So for in DEC last year, so we try to use transfer learning. I think this is another technique for deep learning, deep neural network. Maybe some of you know that. Yeah, it's originally this actually has a pre-trained network that solves the A problem, and for the deep B problem, if the B problem is with some similarity to the A problem, then you can use the pre-trained A network, try to modify the parameter, modify the weight, and quickly to generate a neural net for the B problem. Okay, that's a transfer learning. I think I told you very, very, very high level. Okay, but of course there are several techniques can be used for this transfer learning algorithm. So we typically apply 2 techniques. One is the freeze and train strategy. That means that we freeze all the pre-trained network and only leave the 2 or 3 fully connected network at the end to relax this and to modify that. And another one is we will totally fine-tune the whole neural network. We call it a fine-tune strategy. Okay, so the problem formulation is again like this. We're given the pre-trained network, given the internal structure A by A, and different lengths of the outlet, then we'll do the training. Okay, we'll do a training. The objective try to minimize the loss function. Okay, and also in this paper, I will not go through the detail. In this paper, we also further reduce. We find out we also have some observation which we actually find that we only need the 84 chip to cover all the situation, all the concentration. So then we just we will randomly pick one chip, then we perform the 200,000 benchmark, 200,000 combinations to do the training to have a pre-trained network with a stable with a tuned the weight. Okay, the label are here. Then the rest of the chip, we just need to each chip. We just need we don't need to 200,000 benchmark. We only need 7,000 benchmark, and the network do not need to rebuild. We can just transfer the parameter from the pre-trained network to do the training. So that saves a lot of time. So originally we need remember I say we need 178, right? Remember, days to do this. Right now we only need 2 days, only 2 days to do the database construction. Then again, the following procedure is again, then we build a database. Then you can query if you given I want the concentration 87, 55, and 31% concentration. Then you query the database, and then they'll return you the chip layout. Okay, something like that. Okay, so I think this roughly time. I think I will go through the detail. The loss function. How would it? The loss function here is actually defined. The definition is quite simple, and also the pseudocode. I think is for detail. Please refer to our paper. So here I just want to tell you that we compare the fine-tune strategy and also the freeze strategy, and it turns out the fine-tune strategy is much better. Okay. And also here show some numbers about our experiments. Originally need a lot of time, for the runtime for each chip, and originally we need a lot of data set. Right now we only need few data set to do all the trainings. So I think this is the probably last slide, and we actually in this year we also have another paper. We purely train from the layout. We did not do the transfer learning. We did not do the ANN. We just do we based on this layout, and then we use this combinational convolutional network. We use the two convolutional neural network to do the training. Okay, and we realize that result actually is much better than before. Okay, so actually machine learning is doing a good job. So the paper actually is very lucky that we are selected as a cover paper or Rebang Chip journal this year. So if you're interested, you can look at our paper. So I think this is the last slide. So I just think, I think many researchers are working on the design automation and the control software for the microfluidic. So but although we are not really fabricate the chip, but I always believe that the research in this area is actually one step ahead or the experimental and also fabrication of microfluidic biochips. So recently we also work on different applications for the general purpose microfluidic. We work with the UCLA Professor CJ King. We have developed a tool called the Open Fluidic, and based on my presentation on the digital microfluidic, we already did some we apply reinforcement learning for the digital microfluidic with the Duke University, and also we try to develop some portable device, actually control system for the BGI company for application specific. I think currently we are trying to collaborate with the people from the University of Washington. They try to use the microfluidic chip to do the DNA storage, and for Boston University, we try to do the tool for the synthetic biology application, and with the Tsinghua University in Beijing, we try to fabricate the chip using our tool to fabricate a chip for the application on drug delivery. Okay, so that's all. Okay, Thank you for your invitation. I hope I hope you found this talk.
Yes, sir. So thank
Yeah,
you, Professor Ho, sir. Actually,
yeah,
such nice presentation and such nice discussion about how machine learning technique can be exploited for microfluidics design automation.
yeah.
And through nice simulation, you have shown us that how we can get some desired improvement when we actually exploit such techniques. And also you share with us the present areas of research that are going on currently. So now I ask our audience, please, you can ask any questions or any queries or any doubts that you have directly to
Mhm.
Professor Ho.
Yeah. I can also share the slide if in
Yes,
PDF
sir.
if you need. Yeah.
Yes, sir. Yes, sir. Yes, sir. Definitely, it will help actually all the participants and including us actually, sir. Thank you so much, sir.
Okay.
And
Yeah.
sir, is there any participants who have any questions or queries? Because we are running out of time.
Professor Ho, I have a small question.
Yeah.
Okay. Myself, Topolina Banerjee, I am also working in this field, but I
Mhm.
keenly want to know that whenever this, is there any limitation of number of hidden layers when we map this neural network along with this continuous flow microfluidic biochips, sir?
Mhm. Yeah. Yeah. We in our algorithm, I think in our experiment, we actually try different sizes of the hidden layers, and the sometimes when training the result is sometimes you will. I think it also depends on the how do you define the training data. So if the training data is not good, the even you increase the number of hidden layers, the result will not converge. Sometimes it will overfitting. So actually we did not have a very good observation on how to define the number of hidden layers.
Okay, sir.
Yeah,
And
because
sir, thank you
because
for such a
yeah.
informative talk, sir. It is really grateful.
Oh no. Thank you. I think sorry because I did not. I cannot turn on my camera as I mentioned. The internet quality here is not very good, and even in the previous 2 days, the internet is shut down here, so I cannot do anything. So sorry, the slide I prepared in a hurry. So I think there are many informations that I did not mention in such a short talk, but I will share the PDF slide to everyone, and if you have a further question, I think you can email me or you can find more detail in our paper. So I think the machine learning for microfluidic is a promising area because machine learning, especially for deep learning, can do some prediction. Yeah, so we just showcase one small problem. I would say a small problem, the droplet routing problem, and we are very lucky that we in consecutive 2 years our paper are accepted by ICML, which is a very prestigious conference in machine learning area. So because later on I realized why our paper get accepted because most of the reinforcement learning algorithm they are used for computer games. This video games, playing the goals. This is a very structured problem. But for microfluidic area, the problem is not a structure. So they are glad to see that we can apply such a technique on microfluidic area. Yeah, so I think there are still many application can do, several algorithms can do, but of course sometimes you can feel that the contribution is not come from the problem itself. It come from the how do you leverage the machine learning algorithm to solve this. But even you find out to use some machine learning algorithm to solve our problem, you will find out there are several tedious things to do, and later on you will realize some you will find out some observations why your result is good or not. Then you will try to have some good explanation for the result. I think that's a good things that we can learn. Yeah, it's not purely just I just throw a CNN to our algorithm. our problem, then the result is coming out, and we just buy many GPU, then we can have a result. It's not like that. Not like that. Okay.
Thank you so much, sir.
Yeah.
Okay.
Thank you.
Now I ask our Honorable Vice Chancellor, Sir, Professor Indranil Sengupta, to say a few words about Professor Ho. Actually.
Oh, okay.
So, Professor Ho, I am so thankful to you on behalf of JIS University for sparing your time and deliver this wonderful talk. Means I know many people had this question in mind, why microfluidics has been included in emerging topics in computing. And I believe after your talk, this question has been answered. So you talked about placement, droplet routing, and at the end, your own research in the area of machine learning and reinforcement learning. So now the computer scientists can also see so many wonderful problems that arise out of the sub-problems related to microfluidics. And Ms. I'd be very happy if some of the audience and some of our colleagues get interested to start research in this area, which is a very interesting one. So I'd like to thank you once again. And I'm sure whenever we need your assistance and collaborative help, we would get you by your side.
Okay. Thank you, Professor Sengupta. Yeah, thank you. Yeah, no, it's the pleasure is mine because I'm honored to collaborate with several Indian professors. Originally I came to ISI several years ago. I know the Professor Bhagavat
Yes, I
Bhattacharya.
know.
Yeah.
This is the third talk from you I am hearing. So I had already listened to a couple of your talks earlier.
Yes.
So, and the next talk in this session will be by Krishnendu Chakravarti. So the audience will be much more informed after that talk as well. We are sure.
Yeah. He is the. I sometimes I say, oh, he is the father in this area. He said, no, I don't want to be the father. I don't want to have many children. but he is actually the founder.
And once upon a time, Krishnendu was my student in undergraduate classes long back. Long
really?
back.
Oh, okay. So yeah, he's my close friend and collaborator. Yeah. So
I know.
Yeah. So his talk at night time is also use this link, right?
Okay. Thank you again. Thank you so much again. Yeah.
Okay. Thank you. Thanks for the invitation again. Yeah. Thanks, Professor Sengupta. Okay.
Sir, Professor Ho. So now I ask our HOD sir, Professor Shoikad Maiti, to felicitate Professor Ho. Actually.
Thank you so much, Dr. Kole. Am I audible?
Yes, sir. You are audible.
Yeah. Hi.
Just hold on.
Professor Ho, can you stop the screen share?
Oh, okay. I need to stop. Okay.
Yes.
Sure. Okay.
Is it visible, Professor Ho?
Yeah, I can see it. Oh, wow. You can.
Yeah. Thank you so much for your wonderful presentation. It was really nice indeed. I have listening to it, and for the reinforcement learning, I'm having a bit of interest in that area in artificial intelligence. So definitely, I'll get in touch with you. And thank you once again on behalf of the JIS University, the School of Engineering and Technology from JIS University. And thank you once again for your wonderful speech. I hope in future, definitely we'll get in touch with you for many more reasons related to the research and the other collaborative works. So this is a small token of love and appreciation, as well as a gratitude and regards to you from the JIS University School of Engineering and Technology to you. Please accept it, sir.
Yeah, sure. Thank you so much.
And a small memento for you. Thank you so much.
No, my pleasure. Thank you.
Thank you.
Thank you, Professor Mighty. Okay.
Thank you. So over to Kole.
Okay. So thank you, sir.
Okay. So that's all. Thanks for coming to my talk today, and so keep in touch. Okay. Bye.
Yes, sir. Thank you. Yes, sir. I shall definitely get in touch with you, sir. Okay. Thank you so much, sir. Thank you.
Yeah, you're welcome. Bye.
Bye, sir. Okay. And so participants, so our next speaker, that Professor Krishnendu Chakraborty will deliver his lecture at 4:30. So I request all of you to join with us at least 5 minutes before at 4:25. So till then, you can spare your time in other works. Thank you so much.
And another announcement from our organization side, that all of you will receive another link for today's third session.
I think already that link has been shared to yesterday.
So please join through that link. We
Yes.
are requesting.
Yes, definitely. Thank you, ma'am, for reminding that. Yes.
Okay. Thank you, sir.
Thank you.